Okay, so there we go. All right, so this is sound system design. And this first little bit that we're going to talk about is what we call wave propagation. Wave propagation is, the way that sound waves, we call them waves, propagate through the air, or it propagates through other things as well, not just air. There's a few things you need to know about the way that sound moves. One is that it moves at a somewhat predictable speed. We kind of know how fast it moves. And it'll move at around 1,130 feet per second. If you prefer the metric system, that's 344 meters per second. Although we're going to do most of this math in feet because it's really close to 1,000 feet per second. In fact, here in North Carolina, at this altitude and this typical humidity and everything, it's around 1,050 feet per second, because I've measured it before. So that 1,130 feet per second, that's a moving target. It depends on, altitude, temperature, pressure, barometric pressure. All these things affect the way that sound propagates. So that speed will fluctuate here and there. But generally speaking, around here, it's 1,050 feet per second, which is really, really close to 1,000 feet per second, which means it moves about 1 foot per millisecond, which is really handy. 1 foot for every millisecond. That's a really easy shortcut that we can do now. Pulled apart from each other a little bit, but they can be pushed closer to each other, but they'll always kind of snap back to whatever that resting position was. And so when we hear a sound, what's actually happening is those air molecules are being pushed closer together and then stretched farther apart, and then pushed closer together and then stretched farther apart. And if that happens fast enough and with enough kind of intensity, then it will excite our ears in a way that we will respond to that we call that compression and rarefaction of those air molecules, and that moves the little eardrum, which then sends impulses to our brain that we interpret as sound. So the way it has to happen at a certain speed. So it has to be squished together and then stretched apart, and squished together and stretched apart. And that has to happen fast enough before we'll interpret it as sound. So it has to happen at least 20 times per second on average for us to register that that's something we hear. And anything more than 20 times per second, and anything more than that will be something usually that we can hear, up until we get to around 20,000 times per second. So if it's pushing and pulling up to 20,000 times per second, most of us would be able to hear something. Although I found that that's what the books will tell you, is up to 20,000 times per second. But I've actually found in reality very few people can really hear much beyond 16,000 times per second. You get up to 20,000, and most of you, if we really turned it up, really high amplitude, you might barely be able to perceive something, but it's not a major impact on what you're hearing. Most of what really makes a difference in what we're hearing is going to happen between 63 hertz and 16,000 hertz, I found. But so we call that compression and rarefaction, that pushing and pulling of the air, we call that the frequency. And the frequency, or the rate at which that happens, generally determines what we perceive as pitch. So the difference between like a really low pitch or a really high pitch, right? That's frequency. And that's determined based on how quickly that compression and rarefaction is happening. And so that one full compression and one full rarefaction is we call that a cycle. So hertz is really cycles per second. How many times does it complete one round trip in every second? And one thing I want you to understand is that when we draw this kind of picture, this is a graph. This is not a picture of a sound wave. Sound does not move like this in the air. It doesn't move up and down. It doesn't do that. This is just a graph. This is a graph of air pressure. Okay, so if we're squishing the air molecules together, that would be high pressure. If we're stretching them apart, that would be low pressure. Okay, so this is a graph of pressure. So when we see this graph go up, that means the air molecules are being squished together. When we see this graph go down, the air molecules are being stretched apart. But this is not a picture of what sound looks like. Sound is not going to go up and down in the air, and you can't like duck it, right? You can't dodge it. Okay? Yes.
So this isn't the whole sound wave. This is like one section.
Yeah, it's just a little piece of it. Yeah.
That is going like that.
Yeah. It's going to go on forever.
Okay.
But this is a very super important concept. This is not a picture of a sound wave. Sound does not move up and down in the air. Sound pushes and pulls on the air. Okay, so my voice right now is pushing and pulling on air molecules that are then in turn pushing and pulling on your eardrum. You can't dodge my voice. Okay, you can't move a foot forward and have the wave go over your head. It does not work that way. Okay, and we laugh, but a lot of people have spent a lot of their life staring at pictures like this, and it's really easy to get that idea that that's what sound does, but it doesn't do that. This is just a graph. It's not a picture. It's a graph. Let me see if I can demonstrate this a little bit. So here's a little demo that we put together for my book. I don't know if you can hear it. That doesn't matter. Okay, so let me take this full screen. Oh, wow, it really is zoomed, isn't it? Hang in there. Zoom out. Zoom out. There we go. That's better. Okay, so this is sort of a demonstration of the difference between what we call longitudinal waves and transverse waves. Okay, so that graph is a transverse wave. So here's an example of a transverse wave. This is just me shaking a little string or rope. Okay, it's going up and down and up and down. That's a transverse wave. The idea of a transverse wave is that the direction of the motion, in other words, I'm moving up and down, that's perpendicular to the direction of the way that energy propagates. So I'm moving up and down, but the energy is propagating outwards, okay, perpendicular to the motion that I'm doing. That's a transverse wave. So the displacement is perpendicular to the direction in which propagation is. And this is how we usually graph a sound wave. Even though sound is in the air is really a longitudinal wave, but we graph it as a transverse wave because it's really hard to graph longitudinal waves, as you'll see. So here's an example of a longitudinal wave. So I've got, the little blue dots represent air molecules. So they're everywhere, but we're just looking at a little slice of them, okay? And you can see that I've got a little loudspeaker here that's pushing and pulling on those air molecules. They push, and then they push on the next one. They push on the next one, push on the next one. And eventually, this one gets pushed against my ear, okay? The air molecule itself doesn't, move. It's not like the air molecule that's at my voice doesn't travel across the room and get to your ear. It stays more or less where it is. It just, they just knock against each other, okay? So this is the closest sort of representation I was able to come up with to really illustrate what a longitudinal wave really looks like in the air, if we could see it. Just keep in mind that this is really, it doesn't happen in a column like that. It goes everywhere. I'm just looking at one little slice of it here. But what you notice here is that the direction of motion is parallel to the direction of propagation. And that's the difference. Is whereas in the transverse wave I was moving up and down, but the propagation was outward. In a longitudinal wave, I'm pushing and pulling, and that's the same direction that the energy propagates. It's the same direction that I'm moving. Okay? And that's how sound works. Sound is longitudinal. That energy propagates parallel to the direction that you're moving, okay, moving the energy. Make sense? Yeah.
So when you're recording in a DAW, like Logic or Pro Tools, when you see the waveform, is that representation of sound a lie then? That's not.
It's a graph. It's another graph. It's a graph of amplitude. In that case, it's a graph of how big of a number was encoded at any given point in time. But it's connected to, there were several conversions that happened along the way there, but it is connected to that air pressure amplitude. Ultimately, there was air pressure that was either squished together, high pressure or low pressure, and that excited a mic, because a microphone has a diaphragm just like your ear does. So it pushes and pulls on the diaphragm, which creates a voltage increase or decrease. So high pressure, high voltage, low pressure, low voltage, and then that voltage gets converted to digital numbers. So depending on what the voltage was, when it hit the sound card, it encodes that as a digital number. That's either a really big number or a really small number. And if it's a really big number, that graph will go up. If it's a really low number, that graph goes down. Yeah?
What about, I've heard that when you go to like a concert in the theaters, the best place is not at the front, it's more in the middle. And the way that I thought was the sound just kind of like travels around. That's not it, is it? Because the molecules stay, because you said when you were speaking, they kind of stay relative to where they are. They don't move.
I mean, the only thing I can say is that depending on how, in most cases, with like a live sound reinforcement system like that, they're trying, for reasons that we'll discuss later in a few weeks, they're trying really hard to keep the sound off the stage. They want it to go to the audience, but they do not want it to go to the stage. And so they're at the front row. You're usually like right on the edge of like having it or not having it, because they're trying to keep it off the stage. And if you're close to the stage, then you're close to that area where there's not the sound. Okay, so that's really what it's more about. Is the system is designed in a way to really not deliver a whole lot of sound right there in front of the stage.
Okay.
Yeah.
So since it is, air is everywhere, does
Yeah.
it make it so it's like scientifically impossible to have a completely directional speaker, like perfectly?
Yeah.
A 6 dB drop.
No, you can't really do that. It's not. It's really, unless other than some sort of like, I mean, you can contain it inside of some volume of space. Like, I mean, we're containing the sound inside of this room, so you could contain it inside of a little teeny box, right? But inside of that box, it's going to go everywhere. Okay. So yeah, it's pretty tough to contain it, really. So let's go back to this guy. I've got another one of these little things here that I can show you that might make a little bit more sense to you. You're missing my cool intro music. I know. I forgot to check that before we started. You'll get it next time. So here's another one. So here's kind of, again, kind of try to represent. So imagine the air molecules are everywhere, right? And all we're really going to do is try to just look at a little slice of them, right? But imagine that happening everywhere, okay? So here's, again, what's happening. So there's the compression, okay? When they squeeze together, that's the compression. And there's the rarefactions. Okay, that's the places where they're getting pulled apart. So you put them together, and you've got compression, refractions. Now let's graph this now. So if we were to graph this as a transverse wave, this is what it would look like. So when the wave goes up, that means the air molecules were squished together. When the wave goes down, that means they're stretched apart. So this line that we draw that goes up and down, it's just a graph. It's a graph of air pressure amplitude. Yeah.
Are we hearing rarefactions as well?
Oh, yeah, yeah.
So you hear both?
Well, it is that motion that creates the sound, right? A single rarefaction or a single compression doesn't do anything. It's the motion that excites our ear, okay? So that has to happen a lot of times. It has to happen at least 20 times in a second before you'll notice that you hear it. If it just happens once in a second, you won't hear anything. It has to happen at least 20 times. But reality, much more than that for you to really register that the really low frequency sub bass that comes out of subwoofers is usually between 40 hertz to 60 hertz or so. So that's like 40 to 60 times per second that compression refraction is happening. So you have to have at least that many of these in 1 second before you'll hear it. Okay. Here's just another example of another way to kind of take a longitudinal wave and convert it to a transverse wave. So imagine this spring. So if I stretch the spring, that's a longitudinal wave, right? It's pushing and pulling. The propagation is parallel. But if I then put a little pencil on that little weight that's at the bottom of the screen and start pulling the paper behind it, I will get a transverse wave. So this is effectively what's happening. This is how we're graphing those waves. Okay? So it's just a graph. It's a way of graphing a particular type of motion, but it is not a picture of what's happening in the air. Okay? So most of the time, I'm going to draw that thing, that line, that transverse wave that goes up and down. That's what I'll draw when we do the examples. But I'm not drawing a picture of the sound. Okay? I have had people in places like Best Buy tell me, oh, you got to be really careful where you put the subwoofer because the waves are so big that if you put them in the wrong place, they'll just go right over your head. It's like, no, they won't. That's not exactly what's happening. What they're describing is a standing wave, which is a very different thing. Okay, and we will do a standing wave in this class and let you hear what that sounds like. But when the sound goes away in a certain spot in the room, it's not because that wave is going over your head. That's not what's happening. Something else is happening that is a lot more interesting, actually, and much more plausible. Okay, how are we doing so far? Everybody's with me here? Okay, I haven't left anybody in the dust yet? Okay, we haven't got to the hard stuff yet, but all right. So we've talked about speed, right? We know how fast sound travels. We sort of know this notion of frequency, sort of how many times it does a compression or refraction every second. We know that is about pitch, okay? But we also know that if we know how fast it propagates, and we know that it propagates it has to do a compression or refraction, there's a distance involved in that. Right? It has to travel a certain distance before you've got one full compression and one full refraction. And we call that the wavelength. So the wavelength is the distance between each cycle. So, here's another little picture of my little dots, and I'm measuring the distance between the compressions. That's one full cycle, right? Compression, refraction, all the way back to a compression. That's one cycle. And it had to travel a certain distance in space in order to do that. And that's connected to the speed of sound. And so there's a mathematical relationship to these things, which is this wavelength, that distance it travels, is equal to the speed of sound divided by the frequency. Or if you were to draw that in algebraic ways, it would be wavelength, or lambda, equals c for speed of sound or velocity divided by f for frequency. And the mathematicians tell me that those are the appropriate characters to use for those things. I don't know why, but they are. So you can ask me why, and I'm not going to have the answer, because I don't know. But people who are smarter than me said that's how to do it, so that's how I do it. And I don't know if you guys ever learned this method, if drawing these little triangles like this. I found this very helpful, because if it helps you to kind of do the algebra to convert this. So I know that wavelength equals speed of sound divided by frequency, but I should also be able to figure out frequency should be some connection between speed of sound and wavelength, right? So if I wanted frequency, right? So if I wanted to know f would be speed of sound divided by wavelength, right? Likewise, if I wanted to know the speed of sound, remember I said I measured the speed of sound? The way I did that is I knew the frequency I generated, and I measured the distance that it traveled. And that told me the speed of sound. So the speed of sound is actually wavelength times frequency. So I like to use those little triangles. Again, I am not a super great mathematician. I found that triangle really helps me to kind of do some of those conversions. If that helps you, that's great. If it doesn't, ignore it. You've got some other method, I'm sure, to help you figure that stuff out. Or maybe algebra is easy to you, and you don't need those kind of shortcuts. But I do. Okay. So I'm just sharing you my little tricks. All right. So let's do some of these. Let's do some of this math now. So some of this math, when I say do it in your head, that means no calculator. Let's just see if we can, in our heads, figure this out. And then we'll do stuff with the calculator. So if I said, what is the wavelength of 20 hertz? Remember I said 20 hertz is what the textbooks tell you is the lowest frequency that our ears will respond to. Okay? 20 times per second. What is the wavelength? How big is that wave? How far does that wave travel in one cycle? How would we figure that out? So I'm looking for a wavelength, right? And wavelength equals speed of sound divided by frequency. So I would say speed of sound is about 1,000 feet per second, right? That's what I said. So divided by the frequency of 20 hertz. So what's 1,000 divided by 20? What's 1,000 divided by 20? 50. Okay, by the way, here's my rule. An answer is not right unless 3 people have the same answer. Okay? So I say 50 feet. Deanne said 50 feet. Does anyone else get 50? Okay, yes, okay, it's right. It must be right. Because listen, sometimes I do it wrong too. So it's not right unless 3 of us got the same answer.
So if I use metric, is there a different answer, right?
Yeah, metric would be,
It's like 344.
yeah, be 344 divided by 20. And you would get it in meters. So it would be 340 divided by 20. It would equal a certain amount of meters. Right? Okay, good. We did that one. Okay, what's the frequency of a sound that has a 10-foot wavelength? Okay, so I want to know frequency, and that's going to equal speed of sound divided by the wavelength. So again, speed of sound, 1,000 feet per second divided by a 10-foot wavelength. So what's 1,000 divided by 10? 100, right? So this would be 100 hertz. That's what I got. That's what you got. Anybody else get that?
I got 100 hertz.
Okay, good. There you go. So if you had a sound that had a 10-foot wavelength and it was traveling in the air in North Carolina, it would be 100 hertz. Okay, that would sound like 100 hertz to you and to most of us. Oops. Stop. Go back. There we go. Okay. What about 1 kilohertz? So 1 kilohertz is sort of in the middle of this range of frequencies that we can hear. So I want to know what the wavelength of that is. That would be 1,000 feet per second divided by 1,000 hertz. So that K in kilohertz, that means 1,000. So 1,000 hertz. So 1,000 divided by 1,000 equals 1 foot, right? That's the answer. So let's try another one here. Wavelength of 250 hertz. Think it's 4? Let's do it. 1,000 feet per second divided by 250 hertz. 1,000 divided by 250 is 4. 4 what? Feet. There we go. How are we doing so far? Ready keeping up? Here's another one we should be able to do in our head. Frequency of a sound that has a 5-foot wavelength. 1,000 divided by 5, 200. 200 hertz in this case, right? Correct. Yes. Excellent. Okay, now let's use the calculator. So when I say use the calculator, I mean don't use 1,000 feet per second. Let's use the speed of sound that the textbooks tell you, which is 1,130 feet per second, right? So when I say do it in your head, you can do a rough approximation of 1,000 feet per second. When I say do it with a calculator, 1,130 feet per second, or 344 meters per second. So let's do that. So I want to do, what is the frequency of a sound that takes 50 milliseconds to complete one cycle? Well, I don't want to quite do that millisecond to feet conversion yet on the calculator, but let's just do it in our head real quick. Let's do this one in our head, not in a calculator. Do this whole one in our head. So if it takes 50 milliseconds to complete a cycle, that'll be 50 feet, right? Because it's 1,000 feet per millisecond, or 1 foot per millisecond. If it's 1,000 feet per second, that's 1 foot for every millisecond, because there's 1,000 milliseconds in 1 second. So that's 50 milliseconds would be 50 feet, right? So yeah, do 1,000 divided by 50. And we did that already, right? That's 20 hertz. Yeah? All right. Now we'll do one with a calculator. Okay. Wavelength of a 20 kilohertz tone or sound. Well, let's see what that looks like. So I'm looking for 20 kilohertz. That would be speed of sound, which is 1,130 feet per second, divided by what? 20,000. 20 with 4 zeros, or 2 with 4 zeros. I get 0.0565 feet. So the wavelength of 20 kilohertz is, yeah, really, really small, not even 7 inches. That's really small. Okay? Everybody get that? 0.565? Yeah. Okay, how about this? Frequency of a sound that has a 7-foot wavelength. Anybody want to take a crack at that? What frequency has a 7-foot wavelength? How would I figure that out? 1,130, oops, divided by 7 feet, and I get 161.43 hertz, right? Everybody get that? Yes? Okay, good. This is like the hospital. Doctor, do you concur? Do you concur? Yes, we need at least 2 to concur in order for this to be right. Okay. Wavelength of 3 kilohertz. What would that be? So we would do 1,130 feet per second divided by what? 3,000. 3 with 3 zeros. I get 0.38 feet, right? 0.38 feet. Yeah? Okay, let's try another one. Wavelength of 300 hertz instead of 3,000. That would be 1,130 feet per second divided by 300. 3 with 2 zeros now. All we needed to do is move the decimal place one spot, right? 3.77 probably. Okay? Feet, right? In this case. Okay. Let's see what else we got here. Ooh, here's a fun one. Frequency of a 3-inch wavelength. Oh, wait a second. We don't know how to do this with inches, do we? All right. We only know how to do this in feet, so we have to figure out how to convert 3 inches into feet. So how do we do that? Well, I'll show you the shorthand for the, well, this is the long way to do that. How many inches are in a foot? 12. So what would be 1 foot divided by 12 inches? 1 divided by 12, what would that be in decimal? Like, just do that math. 1 divided by 12. So 0.083. So 1 inch equals 0.083 feet, right? And therefore, 3 inches would be that times 3. So what's that times 3? 0.25. Yeah, so 3 times 0.83 equals 0. I got 249, we could say, really, just to give us an extra thing there. Okay, so that is 0.29 feet is 3 inches. Okay? Now, what's the shortcut for that? Anybody thought of it yet? All you got to do is divide that 3 inches by 12. Right? So any value in inches that I give you in inches, just divide that by 12 and you'll get feet. Okay? Right? Because I took 1 divided by 12 to get an inch, and then I multiplied that by 3. I could just do 3 divided by 12, and I'll get the same answer. Okay? So that's the shortcut. If I ever give you something in inches and you got to get it to feet, just take that number divided by 12. Okay, so 0.29 feet. So let's do the math on that. So what I want to know is what is the frequency of a 0.249 foot wavelength. So if that would be 1,130 feet per second. Oops. 1130 divided by, what was it? 0.249. Okay, I get 4,538 hertz. We could also call that 4.5 kilohertz. Yeah? Either way is right. Did I lose anybody on that one? No? Yeah. Still works the same way. That's the funny thing about sound, as you'll learn as we do this. Sound deals with such enormous ranges of value that close is right. Right? You know? And in fact, my rule of thumb for like grading your work is, could I hear the difference between your answer and my answer? Right? And if no, I could, even though you might have a different number on the paper than I had on my paper, if I could not hear the difference between those two things, then you are right, just like I am right. Okay, so close is right in sound. It's great. Sound is that's why sound is really easy math to do, because you can be close and still be right, even if you're not perfectly exact. Okay.
So, because it's a logarithmic scale, like when we did the, if you did 0.249, we did
Yeah.
0.25, we were 18 hertz away from each other.
Yeah.
But since it was 4520 and 4538, it doesn't matter. But if it was 60 and 78,
You could hear the difference. You could hear the difference between 60 and 78 hertz. You could not hear the difference between those two 4,000 and 2, right? You can, if there's a section in my book about critical bands, critical bandwidth, and we talk about that resolution of our hearing. That as you go up in the scale, that range gets wider and wider, where that range of frequencies that will sound the same to you gets wider and wider and wider as you go up the scale. Even though they're technically different, your ear-brain system has a really hard time telling the difference, because you only have so many little hairs in your cochlea. Okay, like you don't have a hair for every frequency, so it just wiggles the one that's the closest to that frequency. That's the one. That's why you can't hear the difference. Because there could be a range of 100 different frequencies that would, excite that same hair in your cochlea. Okay, so it's just our hearing system is a very blunt instrument. Even
it's to a point where you can't get that, like you
Yeah.
couldn't learn anymore. Like,
yeah,
yeah, okay.
I mean they'll get a point in like Sound Gym where
You can't do better.
yeah, that's why like sometimes even though it'll say perfect, even though you didn't get the number exactly right, that's because effectively it was the same. Like there would be no difference between what you clicked and what the actual thing was, and you would not be able to hear the difference. Okay, that's why it gives you the perfect score anyway. Okay, so here's another one. Frequency of a sound that takes 3 milliseconds to complete a cycle. Okay, I don't know how to do this in time. I only know how to do it in feet. So I got to convert 3 milliseconds into feet somehow, right? So if sound is 1,130 feet per second, we know that, yeah, because I told you that and you just believe me. Okay, I'm not going to prove that. So if I were to, how many milliseconds are in a second? 1,000. Okay, so if I wanted to know how many feet per millisecond, I mean, we know it's about a foot per millisecond, right? But what is it actually if we use 1,130 feet? So we say 1,130 divided by that 1,000 milliseconds in a second. What do we get? What is that? What's 1,130 divided by 1,000?
1.13.
Yeah, 1.13 feet per millisecond. So if sound is 1,130 feet per second, it also is 1.13 feet per millisecond. So if I said it's 3 milliseconds to complete a cycle, it'd be 1.13 times 3, which is what?
3.3.
Yeah, so 3.39 feet. Now what's the shortcut for that?
1,130 times 0.03 or 0.003.
Now if I just wanted to convert 3 milliseconds into feet, what's the shortcut?
If you're using your mind, it's just 3 feet. But if you're using a calculator, it's different.
All you got to do is multiply it by 1.13. And you'll get feet. So because sound travels 1,130 feet per millisecond, that value in feet should always be a higher number than the value of time. Okay? So that 1.13 is a magic number. To convert between distance and time, you're going to do something with 1.13. You're either going to divide by 1.13 or you're going to multiply by 1.13. So distance will always be a bigger number than time. So if you start with time, you multiply by 1.13. But if you start with time, or if you start with distance and want to go to time, you divide by 1.13. So I could take that 3.39, I could divide that by 1.13, and I should get 3 milliseconds again. So just that's a little shortcut. 1.13 is a magic number. If you've got time and you want distance, multiply by 1.13. If you've got distance and you want time, divide by 1.13. Okay? So now I know that it is 3.39 feet. So what frequency is that now? So that would be 1,130 divided by 3.39, yeah? What does that work out to? Hertz. That's what I got. Anybody else get that? Yes? Okay, good. Perfect. We did it. Everybody still with me there? Any questions about that? Did I lose anybody? Okay. There's a lot of traversals there, so speak up. Okay, that's it. We're done for today. We don't have time to go into resonance. So, questions? Okay, so this is about how this class will go every day. Okay, we're going to come in. I'm going to shout a whole lot of math at you, and you're going to try to understand it. And then I'm going to send you away to practice it a little bit. So after the class, I'll email you a little PDF or something that'll say, hey, here, do some of those kind of questions we just did. I'll have you do them on your own. And there'll be stuff on there that you're not going to know how to do yet because we haven't talked about it yet. Okay, so just answer the ones that you know how to answer, and the ones you don't know how to answer, you haven't done anything wrong. You didn't miss anything. We haven't talked about that yet. Okay? So when I say, oh, calculate the comb filtering for two sounds with a 1.5 millisecond difference between them, you don't know how to do that yet. I haven't taught you, so don't worry about that. Okay? Yeah?
So I didn't take pre-calc or calculus.
Neither did I.
I don't know what sine wave is, like what a sine wave is.
I don't know either.
Okay, cool.
Doesn't matter.
Okay,
It does not matter for our purposes. Okay? It's enough for us to know that they exist.
I like that.
Okay?
That's a good answer.
I mean, it matters, I imagine, in some situations. It does, but it doesn't matter for us. We don't have to calculate a sine wave ever in this class. We just have to know that such things exist, and we have to know that you can change it by some way, and it'll result in some different value. But we don't have to ever graph that value. Because remember, the sine wave is just a graph, okay? But we don't ever have to actually do the graph. Because all we care about is what we hear.
So, one question I did have, when you said that in North Carolina here, you calculated it as 1,050 feet.
Yeah.
In reality, it should be 1,130 feet.
Yeah.
Does that ever have an impact on us? Like if we were
Oh, yeah.
doing delay speakers,
Oh, yeah.
you need to know that.
Yeah, definitely. So speed of sound is a moving target. A little bit. I mean, it doesn't vary usually by a whole lot, but it's usually hovering around that 1,000 feet per second area, a little bit more than that. I've only ever been in one situation where it was so vastly different that it was screwing me up. And it was one time, actually it was during an intensive art several years ago, and we went up to this place in Boone, North Carolina, where they had this old movie theater that they were trying to renovate into a performance venue.
Is it in West Jefferson?
I don't remember. But I remember we went there in December during intensive arts, and it was just an empty, gutted room, rectangular room, basically. And they wanted us to do an acoustic analysis of it to help them know what should they do to the walls to kind of help it work better for a live performance venue. And so we were doing measurements, and none of the measurements were making any sense. We were using smart analysis software to measure the sounds in the room and look at the impulse responses, to look at time and frequency, and nothing was added up. Was that?
Like what we did at the church.
Yeah, like that. But it just none of the things we were seeing on the computer made any sense based on what we were seeing in the room. What the computer was telling us was not lining up with what we saw. We could do that kind of math in our head, and we'd say it should be about a 10-foot path, but this room is a whole lot bigger than that. We couldn't figure out what was going on. And the reason is it was December. It was a snowstorm. It was really, really cold, and they didn't have a heating system in the building because they'd gutted the whole thing. So it was super cold. It was so cold that the speed of the sound had slowed down. It had slowed down considerably. Maybe probably a little bit, but sound had really slowed down so much that none of our measurements were making, because we had to tell them like where to put walls and how big those walls could be, and and we kind of came out of it going, we don't actually know. Like we can give you a kind of a guess, but if you really want to know, we need to come back sometime when the heat's on, because it's like none of what we're seeing is making any sense. So
does temperature or altitude have a bigger impact?
Temperature, usually, in my experience, usually. Yeah.
So it's something that can affect it, but like you don't need to measure the sound in every, like the speed of sound in every venue.
No, you don't need to. Generally, it'll be, that shortcut of 1,000 feet per second is usually pretty darn close for most.
Because if a delay speaker is a millisecond off.
Yeah. Yeah. Usually. Okay. Other questions? All right, so we are done. So I will send you a little bit of homework to work on. You don't have to have it done by Friday, but because the whole thing's not due until whatever day I set in the syllabus. But it'd be good to kind of start practicing this stuff. The whole idea is to kind of do some more of this so it becomes easy to you. Because especially the ones that we do them in your head, because that's a good skill to have, to be able to just walk into a room and go, oh yeah, it should be about this, just from looking at it and guessing in your head, right? Okay.